Hello, thanks for joining us on Space Nuts, where we talk astronomy and space science every week. My name is Andrew Dunkley, your host, and so glad you could join us. Coming up today, we'll be talking about magnetic fields and do they exist on exoplanets. We'll also be talking about something quite extraordinary, the flattest explosion ever observed in space, and it was big too. And sad news about Virgin Orbit. We'll also be answering audience questions about sending high-speed satellites into the solar system and the density of gas. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to talk Turkey again this week, the Turkey constellation that is Professor Fred Watson, astronomer at large. Hello, Fred.
Good day, Andrew. Turkeys are, there isn't a Turkey constellation. There should be, really.
There should. I'm sure there's some cluster out there that looks Turkey-like.
Yeah. Well, actually, for most constellations, it doesn't have to look anything like what its name is anyway. So take your pick.
No. Well, the country of Turkey could use a bit of an uptick at the moment. They've had a pretty rough time of it. Why not? Why not the Turkey constellation?
For Kia now.
Yes, that's true. You're right. Yes, absolutely. How you been?
Oh, well, thank you. Yep. Still pushing back the frontiers. Well, so much the frontiers of knowledge as the frontiers of bureaucracy.
Yes. Yes, there's a lot of that.
Yeah. We had a nice event last week when a virtual reality movie of the site in Western Australia where the Murchison Radio Telescope is, or where the square kilometre array will be, a virtual reality movie of all that, showing you what it's like there and what kind of landscape it is. And that was launched at the National Museum of Australia in Canberra on Tuesday night, I think it was. At which I gave a little talk about astronomy and all the other stuff. And one of my colleagues, Ant Schinkel, who's a specialist working with the SKA, he also gave a talk. And then we had this view of the virtual reality tour, which is astonishing. It's my first real experience with decent stereo glasses of a virtual reality movie. And yeah, you've got a 360-degree view. You turn your head round and you see behind you.
Yeah, we did that at Easter. Nothing to do with astronomy, but there's an escape room in Dubbo, which is very popular, and they've brought in a virtual reality experience. So I did that with my boys at Easter too. It's the first time I've ever done it too. It's a bizarre thing, but it's a lot of fun. It's a heck of a lot of fun. Yeah.
No, this is a fantastic production as well. It's really well done. It will certainly be circulating more in Australia and maybe globally. Some of our overseas listeners might find it coming up. It's called Beyond the Milky Way.
Okay. Sounds good. All right, let's talk about what we came together to talk about today, amongst other things. I mean, we don't always stay on track. Occasionally we might drift, just occasionally.
Be like us, would it?
No, not at all, really. But we know about Earth's magnetic field and how important it is to, basically protect us from all the evils of the universe and to keep our atmosphere intact.
Yes.
So the question has been raised, do you find magnetic fields on exoplanets? Now, this is a very important question because obviously if we're looking for life out there, we probably need to find a planet that has a rocky surface with probably water or something similar, and it would have to have a magnetic field, would it not?
But yes, it probably would be an important component because exactly as you said, the Earth's magnetic field protects the atmosphere. It also protects the surface from the more energetic subatomic particles that are floating around in space, many of which are launched from the sun with its solar wind and occasional solar flares. We are largely protected, not entirely, but largely protected from the effect of those things on the Earth's surface by the Earth's own magnetic field. So yes, the question is, do rocky exoplanets have magnetic fields? Now, I have to say that I would assume that the answer to that is probably yes, because planets tend to be made in the same way, no matter where in the universe they are. And rocky planets probably usually have, like the Earth does, a core made of iron and nickel, and that is what generates the magnetic field. It acts like a dynamo and generates the Earth's magnetic field as the Earth rotates. So you'd think that the answer would probably be yes to the question of, do rocky planets around other stars have magnetic fields? And so observations have been made with the Carl G. Jansky Very Large Array, which is a telescope, an array telescope in the United States, one of the biggest in the world, actually. I've visited it. It's quite an extraordinary place, operated by the US National Science Foundation's National Radio Astronomy Observatory. And so observations have been made by scientists of a star called YZ Ceti, which is a star that actually emits radio signals. Now, not all stars do, but this one does.
Yep.
And what the scientists have done is used the radio signals coming from this star, which is about 12 light years away, so it's a close star, to interpret what is happening to its planet, because we know that YZ Ceti, I should say YZ Ceti, shouldn't I, just for our American listeners?
Potato.
That's the one, yes. Is YZ Ceti B is a known planet orbiting the star.
Yep.
And what has been observed are sort of bursts of radio waves, which are to do with the interaction between the star's magnetic field and the planet going round it. Now, the good thing about this planet is it goes round once in 2 days.
Oh.
So it's very close to its parent star. And that means that there are probably, magnetic interactions taking place between them if the planet has a magnetic field. So to cut the long story short, these bursts of radio emission have been analysed, and there is enough evidence that they are that the scientists in question are convinced that what they've proved is that the planet YZ Ceti B has its own magnetic field. So there are a number of different scientists involved with this, including the director of the National Radio Astronomy Observatory and astronomers from Bucknell University and the University of Colorado. So quite a disparate group of principally US scientists who've been looking at this. And some very nice quotes from those scientists. One of them who says, "I'm seeing this thing that no one has seen happen before," which is always a nice thing when you're a working astronomer and you're sitting at a big telescope somewhere and something turns up. We saw the initial burst and it looked beautiful. This is a quote from another of them. When we saw it again, it was very indicative that, okay, maybe we really have something here. So what they're saying is that as this planet goes round its star, they have it interacts with the magnetic field of the star in such a way that you get bursts of radio energy, and so in fact, so let me read another quote from one of the scientists. What we're doing is looking for a way to see the invisible magnetic fields. We're looking for planets that are really close to their stars and are similar in size to Earth. These planets are way too close to their stars to be somewhere you could live, but because they're so close to the planet, it's kind of ploughing through a bunch of stuff coming off the star, and that's the equivalent of the solar wind that we have in the solar system. If the planet has a magnetic field and it ploughs through enough star stuff, it will cause the star to emit bright radio waves, and that's what they are interpreting these bursts as being. In fact, they've kind of coined a new phrase, which is really nice: extrasolar space weather. Space weather beyond the solar system. So when we think of space weather, we think of the environment of the Earth principally, but the subatomic particles within the inner solar system that come from the sun. And space weather's actually it's a big issue. In fact, I was talking to one of my colleagues in the space agency yesterday about exactly this: how you deal with space weather.
Yeah.
Probably in a legislative fashion, because that's what a lot of what the space agency does. But you've got to make the rules. So how does it work? What's the story with it? Anyway, sorry, go ahead.
Yeah, I don't mean to throw a bucket of water over the discovery, but should we be surprised that exoplanets probably have magnetic fields? I mean, we were surprised when we found the first exoplanet, but we always thought there'd be one, and now we've found thousands. So it stands to reason that a lot of them would have magnetic fields as well.
Yes, and that is certainly true, and it's already been established with the bigger ones, like the hot Jupiters.
Yeah,
that's been established that they do have magnetic fields. These things are bigger, brighter, beefier in every way, and so things like that are easier to detect. The crucial thing about this is that this is a rocky planet, an Earth-like planet in terms of size, and that's the difference. But as I said at the beginning, you might well expect it, given that if it's a rocky planet made like the rocky planets in the solar system, it will probably have an iron core, which will give rise to a magnetic field. On the other hand, here's a counter-argument to that, Andrew. Venus doesn't. And neither does Mars. So there are two rocky planets in our solar system, which are quite nearby, that don't have magnetic fields, and certainly not magnetic fields today. Now, Mars is thought to have had a magnetic field, but it's lost its magnetism because it's too small for that to be sustained by the core of the planet. The planet's cooled down too much. Venus is a different kettle of fish, though, because it's Earth-like.
We're almost the same size, aren't we?
Yeah,
Earth and Venus.
Right. Yeah. So if Venus doesn't have a magnetic field, then it's not a foregone conclusion that any rocky planet is going to have a magnetic field.
Yeah.
So that's the issue. Now, there is one twist to this story that I found fascinating. And that is that magnetic fields, when you've combined them with a solar wind, and that's what we're talking about with space weather, that's what produces the aurorae on the Earth, the northern and southern lights, the aurora borealis, the aurora australis.
And we see them on the gas giants too.
We do, yeah. All the gas giants have aurorae as well.
Yeah.
Now, aurorae can be detected in radio waves as well as visible light. That's the crucial thing. So you can know about aurorae from radio astronomy. And it turns out that this YB SETI system has aurorae, but what they're actually seeing is aurorae on the star.
Oh, what?
Yeah.
Wow.
Interactions between the magnetic field and the wind of particles coming off cause magnetic disturbances, which they can identify as being due to aurorae, even though we can't see them. But they also think that if the planet has its own atmosphere, and that's certainly not something that's known, but if it did, that would also have aurorae.
Quite incredible.
Yeah.
So that's another thing. Aurorae could be a very common thing in the universe too, sounding like it.
Yes. Yeah, that's right. Indeed.
Wow. That's quite a discovery. See, I didn't tip water on them. I just...
Oh, no, you didn't. You
brought up an angle that created more information.
More information. That's correct.
Yeah, right. Okay.
It's always good to be skeptical of these things.
I'm an optimist when it comes to astronomy.
So am I.
Yeah, indeed.
Actually, I'm an optimist when it comes to pretty well everything, I have to say. It really annoys some people.
Well, yes, but they're pessimists. But if you want to chase up this story, you can go to one of our favourite websites and read up on it, phys.org, Phys, by the way, phys.org. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Now, Fred, this one fascinates me because this is only a fairly recent discovery in terms of what we're talking about. It only dates back to, I think, 2018 when they first spotted one of these. They're called an FBOT, FBOT, and basically we're describing a cataclysmic explosion in space, but they're different from an explosion as we know it. Now, most explosions sort of go out in all directions simultaneously. This one didn't, and they've just discovered another one, and it's one of the biggest or flattest explosions ever observed.
Yes, that's right. So yeah, the FBOT, an FBOT in this instance is a fast blue optical transient.
Yeah,
It could also stand for a fantastically big optical telescope.
it could do.
But it doesn't. It's a fast blue optical transient. And so that kind of tells you about it. It's optical, so you see it's in visible light. It's blue, because that's the wavelength range, the blue wavelength range that it emits its light in. It's fast, because it comes and goes very quickly. And transient just is referring to the fact that it is something that is not permanent. It's temporary or transient in its nature. This is a star in another galaxy. A galaxy about 180 million light years away. So it's not part of our local group of galaxies, which goes out to about 5 or 10 million light years, perhaps a few more. But this is an explosion of a star that has some that has some difference from what we normally see. Normally, when you see an exploding star, Andrew, as you well know, it's a supernova.
Yeah.
It's a star that's got to the end of its life, run out of hydrogen, run out of everything it needs to burn in the normal way.
Didn't pay its tolls.
Yeah, didn't pay its tolls, all of that. And, everything has come to an end and it collapses. And in the process of the collapse, you get this huge emission of energy as it winds up becoming its core becomes a neutron star or perhaps a black hole. But this is something different, and it is, I have to say, not clear how these FBOTs work.
Okay.
Scientists, and this study's been done mostly by British scientists, don't really know what causes fast blue optical transients, but they can observe them. And this particular one has been observed with a smallish telescope, and it's actually one I know quite well because whilst it's not the one at Siding Spring Observatory, which is called the Las Cumbres 2-meter telescope, this is called the Liverpool telescope. So it's Liverpool telescope. It's a 2-meter diameter telescope, and it was made by sort of corporation in Liverpool in the United Kingdom. In fact, they made about 5 of them, I think. One came to our observatory here in Australia. One went to the island of Maui in the Hawaiian chain. And one called the Liverpool telescope is actually on La Palma in the Canary Islands. That's an island, again, that hosts large telescopes on one of its volcanic peaks. I used to work there a lot during the 1990s. Mm-hmm. So the Liverpool telescope has a piece of equipment on it which is specialized in the world of astronomy, but very, very powerful in terms of what it can tell you. And I'm kind of friendly with scientists here in the University of New South Wales who use similar equipment. These are called polarimeters, and they measure polarization, not just the brightness of light or its color, that's to say its wavelength. They also measure whether or not it is polarized and what the amount of that polarization is. And we kind of know about polarization from polarizing sunglasses.
Yeah.
The idea being that the vibrations of light waves when the light is polarized, they sit in one particular plane, or sometimes they rotate actually, which is a bit more complicated. But it's essentially the equipment that's on the Liverpool telescope is the equivalent of a pair of polarizing sunglasses, so that as you rotate them, you see different intensities. In the case of polarizing sunglasses, it's to kill the reflections coming off a road or a bright surface, which you can do by blocking out that polarization of the light.
Yeah.
So you can do something similar in astronomy. And now polarization is caused by principally emission from dusty particles, things that have got an alignment to them, that they're perhaps shaped like a pencil or something like that. And if you've got lots and lots of particles of dust that are aligned, for example, by magnetic fields, you can work out from the polarization where those magnetic fields go. I'm not explaining this very well, but it lets you determine some structure in a source of radiation that you wouldn't otherwise be able to see. And that's how, just by looking at the light that's come from this FBOT, these scientists can tell that there is a flat disk of material around it, as you said, the size of the solar system, which is the result of the explosion. Something has exploded, and it's exploded not in a spherical fashion like we expect everything to do, including supernovae. It produced a flat disk of material, and that is a mystery. How does, first of all, how do these things work?
Yeah.
And secondly, how does it create this flat disk? There's a scientist, the lead author of this study, who's actually in Sheffield, in the north of England, University of Sheffield's Department of Physics and Astronomy. Dr. Justin Morn says very little is known about FBOT explosions. They just don't behave like exploding stars should. They're too bright and they evolve too quickly. Put simply, they are weird. This new observation makes them even weirder. There's a little bit more, perhaps I can read from Dr. Morn. Hopefully this new finding will help us shed a bit more light on them. We never thought that explosions could be this aspherical. There are a few potential explanations for it. The stars involved may have created a disk just before they died, or they could be failed supernovas where the core of the star collapses to a black hole or a neutron star, which then eats the rest of the star. What we now know for sure is that the levels of asymmetry recorded are a key part of understanding these mysterious explosions, and it challenges our preconceptions of how stars might explode in the universe. We never thought that they'd go off bang with a flat disk. So,
Yeah, you always think of everything that explodes in the universe as going out in all directions simultaneously, spherically. May I ask, and I don't presume to be sort of, again, tipping water on their observations and discoveries, but could it be we're only seeing part of the explosion and that there is, in fact, a spherical outburst and we just can't see parts of it? Or are they pretty certain this is a dead flat type of explosion?
That's a really interesting comment, Andrew. Well done. And you should write to these people and tell them that, because there are things in the universe where we think we're seeing something, but what's really happening is that we're not seeing the whole picture. And often it's a dust cloud or something like that is blocking our view of what else is there, if I could put it that way. So it's possible, you could imagine that, yes, something like a dust cloud could be blocking our view, and all we're seeing is the flattened exploding disk. I think what knocks that on the head.
Okay, fair enough.
So maybe you shouldn't write to them. Is that the way they've detected this is by polarization. And I suspect if it was just a spherical explosion and part of it was being blocked off, we wouldn't have that phenomenon. It wouldn't be, the light wouldn't be polarized. So it's something to do with the actual structure of this disk of material that gives you the polarization, and that is telling you that it really is a flattened disk of stuff that this star's emitted, rather than a blocked off view of something more symmetrical.
Yeah, and the other interesting thing is that, like many things we've talked about recently, this is a fairly new discovery. As I said at the start, the very first one of these was only discovered in 2018. So this is a whole new realm that we're, again, trying to understand. It's right up there with the dark matter and dark energy and even black holes. We don't really understand a lot about them. This is another one.
Yeah, that's right. And of course, that's the great thing about astronomy. When something new like this comes up, it sends the theoreticians back to their drawing boards, scratching their heads. How can we account for this? How can we explain what's going on here? So it pushes physics along as well to try and understand what actually is happening.
Yes, indeed. Okay, that's on the phys.org website as well. But if you want to do some deeper reading about it and read 500 pages of authors, go to the monthly notices of the Royal Astronomical Society. That's where you'll find the paper on FBOTs. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying was a go.
Space Nuts.
Now, Fred, before we go to questions, this is a story that came as quite a surprise to me, and this is only a recent announcement, but some bad news for Virgin Orbit.
Yes, that's right. So Virgin Orbit, which is, a spin-off really from Virgin Galactic, and you remember their stock in trade is the launch of orbital vehicles using a converted Boeing 747 to carry a rocket up to 40,000 feet or thereabouts, whereupon the rocket's dropped and it ignites and off it goes to launch payloads into orbit. It's got marvelous advantages, actually, because you can do launches at short notice. You can launch from anywhere. Basically, you don't have to be, on a continent. And you would have thought that would have been a very commercially attractive thing, and would have, naturally resulted in a company at least staying viable and probably doing very well. But what seems to have happened is that because of SpaceX now being able to essentially bring down the cost of launch by actually recovering their launch vehicles and using them again. We've talked about this many times, the fact that SpaceX's Falcon 9s can be used up to about 20 times now.
Yes.
And that's brought the price down. And the suspicion is that has made Virgin Orbit less competitive. Plus, they had, sadly, their last launch didn't work. We covered it, actually. It was earlier this year, where the rocket, I think the second stage failed because of a filter that was blocked. This was a launch made from southwest Britain. From the aircraft took off and launched over or off the shore of Cornwall. So, unfortunately, the satellites that were launched didn't make it. They didn't make the second stage because of that filter issue.
Yeah.
And so that's very sad. And that might kind of be the final straw that's caused this company now to file for bankruptcy.
Very sad.
Yes, very sad. Especially for us in Australia, because I think the next launch was planned to take place from one of the airfields in Queensland, in Toowoomba.
That's right. I remember that.
To launch from there.
Yeah, it would have been very exciting for the city. Toowoomba's a beautiful place.
It is.
It's a real pity. This doesn't have any impact on Virgin Galactic at all, though, does it?
Not as far as we know. Virgin Galactic's gone quiet at the moment. After, I think, the first flight, if I remember rightly, I can't remember whether that was last year when Branson flew on the rocket plane. But we're still waiting for fare-paying passengers to be launched up there.
Yeah, all right. There'll probably be more on this down the track.
Yeah.
Okay, Fred, let's get to some questions. Got a couple of text questions today. Hey, Fred and Andrew, long-time listener, first-time caller. And I was wondering why we haven't seen or heard of more exploratory missions where we send a satellite at extremely high velocity out towards objects in the solar system or perhaps beyond. given the rapid advances in technology, is it feasible to do fast science in space? I assume the fastest man-made object is also space related, and any idea what the fastest man-made object is, and the implications of high relative velocities in space and the impact it has on said object and the data that we're able to collect. Being Expanse fans, I recall a character racing around the solar system, and being a gearhead myself, this topic is near and dear. That's from Michael in North Dakota, far North Dakota, he makes a point of saying. Look, we've done a few missions out there, and of course you think of the Voyager probes, which are still going, even though they're having to shut things down bit by bit to keep them alive. But why haven't we done more? Why can't we, with the current technology, just go boom, send something out at super high speed and do some exploring?
Yeah. So the technology is it is advanced, but you're still limited by the physics of the chemistry of rocket propulsion and the physics behind it. The fastest launch, I think I'm right in saying this, was New Horizons.
Yeah.
Which had to be quickly boosted to a velocity that would take it past Jupiter, so that it got a slingshot out to Pluto. It was launched in 2006. It flew by Pluto in 2015, and is now escaping the solar system. It's had its rendezvous with Arrokoth, that strange little double asteroid that was in the headlines the beginning of the year before last. I lose track of these things. It might have been the year before that. I think 2021, I think it was.
Yeah.
So that's the nearest thing to what Michael's suggesting. And that really pushed the technology to get New Horizons up to that high initial launch speed. I suspect he's right that the fastest human-made object is a spacecraft. I'm trying to think of terrestrial experiments.
The Helios satellites, apparently the first two satellites designed to study the sun travelled at 157,078 miles per hour. I'm told they're the fastest ever man-made objects in space.
Okay.
And the fastest object on Earth, you're going to love this. This was during a nuclear bomb test called Operation Plum Bob. And Robert Brownlee was asked to design the test, and he put a cover over the test point, the test tube, if you like.
Yes.
And he wanted to test the speed of the manhole cover when the explosion happened. And I don't know exactly how he did it, but it came out. It got blown into the stratosphere at 125,000 miles an hour. So that's the fastest Earth-based man-made object, as far as I can tell. That's just a quick search I've done. But and I think one of the fastest objects that carried a person in space was Apollo 10 capsule at 24,791 miles an hour. That's quick.
Yes. I never think in miles an hour, Andrew.
No, I'm trying to convert it. But
converting these to kilometres per second.
Yeah.
So that last one's about 11, I think, which is actually the escape velocity of Earth.
Mm.
I love the manhole cover.
That's a great story.
The fastest spacecraft as we speak today,
yep,
however, is Voyager 1, which you mentioned earlier, which is still travelling away from the sun. It's just under 17 kilometres per second.
Mm.
And that's the, in terms of something that's ongoing, that's the fastest human-made object. It's moving away at that speed, and will keep going forever, probably, pretty well. So
until it hits something.
Yes, or not. More likely to go into orbit around something. If it winds up in a foreign solar system. On the other hand, it could fly through a solar system a bit like Oumuamua did and baffle any sentient beings that are out there.
But
Anyway,
it could get caught in the orbit of another planet, because we've had that happen here with Earth. We had a second moon there for a little while. It might still be there, as far as I know.
Yes, that's right.
Tiny little thing.
So Voyager 1 certainly holds the record at the moment as being the fastest spacecraft flying. If it was on its way to Proxima Centauri, it would get there in 74,000 years.
Yeah, so that kind of makes the high-speed technology of today still fairly redundant in terms of long-haul space travel, unfortunately.
Indeed it does.
Okay, thank you, Michael. Let us move on to our next question from another Michael, who calls himself Mike. He's from Brisbane. Hi, space nutters. The density of gas in the vacuum of space. We're always talking about and looking at gas clouds in space. So my question is, what is the density of gas in between the planets of the solar system? What is the density of gas in between the stars and the galaxies? What is the density of gas between galaxies? Also, what is the density of gas in a typical nebula? I'm assuming the answer will be X number of atoms per cubic meter, with X being a small number. Regards, Mike. It's a good question.
It's good, and Mike's given the answer as well.
Okay.
So it's a small number of atoms per cubic meter. I've got a feeling that when I wrote Spacewalk, was it Cosmic Chronicles? I think I talked about this stuff right at the beginning. I can't remember. Said he reaching for one of his own books.
Well, if it's in there.
Yeah, it might be. It might be easy to, because I talked about finding yourself in a typical place in space.
Yeah. I think we've raised that before.
And the answer is, it's dark and it's cold and it's empty. And somewhere, I thought I'd given how many atoms per cube. Here we are. If you're lucky, all right. This is in normal. It's in a typical location. So it's between the galaxies. It's not in a solar system. Mm-hmm. This is in the depths of space. If you're lucky, you might find one atom of hydrogen in the volume of space normally taken up by 15 adults, a cubic meter. There you are.
Wow.
So that's typical, or typical of the intergalactic space, one atom per cubic meter. And it goes up from there with, I guess, the nearer you are, if you're in the interstellar medium in our galaxy, it's significantly higher. It's probably measured in tens of atoms per cubic meter. The solar environment is rather more populated. It's probably hundreds of atoms per cubic meter, but it's still a vacuum to all intents and purposes.
Yeah,
I'd have to look up the numbers, and I'm sure Mike is as capable as I am of doing that to find the density of the things to look up: interstellar medium, solar wind, those sorts of places. That's where you want to find the numbers. The exact numbers. But it's small, it's tiny.
If you were to talk about one of those beautiful nebula, like the Horsehead Nebula or something, what would be the density in something like that?
It's still extremely low.
So you could fly through. You could fly through it.
Absolutely. Yeah. It's
wow.
It's very low. There's an adjunct to that, a little story in the history of astronomy, and it kind of illustrates how low these nebula densities are. Because when nebulae were first observed with a spectroscope by a man called William Huggins back in London in the 1860s, he found emission, and it's the kind of optical fingerprint of gases that we use to work out what's in space.
Yeah,
he found these what we call emission lines, this fingerprint of some gas that was completely unknown on Earth. And they actually called it nebulium because they thought they'd discovered a new element. That was in the 1860s. And nebulium was one of the huge mysteries throughout the latter days of the 19th century. into the first couple of decades of the 20th century, because it got to be an even bigger mystery, because by then the periodic table had been invented and there were no gaps where there could be this Eulium thing. And it was a man called Ira Bowen, who was an American astronomer, later became the director of Lick Observatory, if I remember rightly, who worked out what it was. He'd had some hints by some comments by another astronomer before him, but he figured out that what we were seeing was emission from a normal gas, but at a very, very low pressure, where the atoms don't bump into each other at all, which is what you get in a nebula. There's hardly any bumping of together of atoms. It's my God.
Oh, hello.
Yeah, Andrew can't talk to you because I'm on there.
Yeah, you can't hear me. Yeah,
I'll leave you to it. Hi.
Actually, we're nearly done. Yeah, so it's just that was when they recognised that this was nearly a vacuum, and the atoms are so far apart they don't interact, and that gives you this different signature for what is an otherwise normal gas. In fact, those spectrum lines are called forbidden lines because they're forbidden on Earth.
Right.
They're not in the depths of space.
Fascinating.
I once wrote a poem about it called Forbidden Lines. Maybe I should read it one day.
Maybe you should. Maybe you should. Yeah. Okay. There you go, Mike. I'm sure you're glad you asked the question. You knew the answer by the sound of it. Yes.
Yeah.
Very good. Don't forget, if you do want to send us a question, you can go to our website, spacenutspodcast.com or spacenuts.io. There's a little tab up the top called AMA, or a link if you like. You can click on that to send us audio or text questions, or you can click the Send Us Your Voice Message tab on the right-hand side. And don't forget to tell us who you are and where you're from. And while you're on there, have a look around. There's the Space Nuts shop. There's the Astronomy Daily newsletter, which you can sign up for and get a daily dose of astronomy and space science. You can learn about supporting Space Nuts by becoming a patron. It's all on our website, spacenutspodcast.com. Fred, that brings us to the end of another episode. Thank you so much, sir.
It's a pleasure, and I'm sure we'll do it again sometime.
I reckon we will. Sometime soon, I hope. Yeah. Okay. Take care. We'll talk to you soon.
Sounds great. Thanks.
Fred Watson, astronomer at large, part of the team here at Space Nuts Central. I'll call it that from now on. And thanks to Hugh in the studio. For what, I don't know, but thanks anyway. And from me, Andrew Dunkley, thanks for your company. Looking forward to joining you again on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.